Okay, so you should see my screen now. I hope you see my screen. Do you see my screen?
Yes.
Yes.
Okay. Welcome to our meeting today that is organized in the form of a webinar. Thank you. In the form of a webinar entitled NTN Service Continuity for Machine-to-Machine User Traffic. I am Giovanni Giambene, co-chair of this group. Okay, so this webinar will deal with the integration of TN and NTN service continuity. It will address IoT and user scenarios and discuss future directions. I'm very happy here to introduce very quickly, the activity of our working group. We have of course, we focus on satellite network because they can cover areas that cannot be addressed by terrestrial network, like high-speed aircraft airways. And this is very important. We consider satellite at different altitudes, GEO, MEO, LEO, high-altitude platform, and unmanned aerial vehicles. We also address IoT, not only broadband traffic, and we also focus and follow the development of the standard in releases 17, 18, and following one. And our main aim is to focus on the challenges and solution for NTN in the coming years. The co-chair, Dr. Sastikota, myself, we have more than 50 participants from many countries, as you see here. We have this webpage, and we meet every 2 weeks on Wednesday at this time. And if you like to join the group, you have to email us, and we will, of course, we'll be happy to have you in the group. We published the 5th edition of the satellite report. This is available as a pre-publication on the webpage of this Future Network website, and it will be available on IEEE Explorer. In this document, we address architecture use cases, including Open RAN, physical layer, millimeter wave, optical wireless, antennas, artificial intelligence applied to satellite, mobile edge computing, security, network management, and the standardization aspects. So we have a broad coverage in all these topics. And we also monitor the development of the system. We also focus on current trends and the IMT 2030 objectives. In particular, we highlighted that current LEO, mega LEO system are currently approaching the performance of terrestrial system in terms of downloading, uploading, and latency. Here we have US statistics of 24, but also the trend of is always improving. So also in 2025, in this year, basically, all these KPIs are even better. So the satellite system are really close to terrestrial one. In this group, we focused on many topics. In particular, one of the most interesting, in my opinion, is routing for mega LEO, based on IS technique for multi-hop routing, using the area proxy concept, MPLS for the forwarding plane. And the idea is to exploit routing pre-computed updates, taking into account the prediction of the LEO constellation. This allows immediate handover and avoid buffering and consequent latency and packet loss. So in any case, you will have, this is just an example. Very quickly, you will find more detail in the satellite report. And we continue in this, with this activity, focusing in the next report on other topics like direct connectivity, broadband, including UAVs, broadband in different scenarios, energy efficiency, user mobility, virtualization, and the progress of the standard. So this concludes my introduction. Of course, before I give the floor to the presenter, let me just show the two talks that we have. The first one is provided by Remcom USA, Greg Skidmore and Tarun Chawla. Sorry for my pronunciation. The topic is simulating use of LEO satellites to extend NB-IoT coverage to rural areas. And here you have the abstract, and for sure they will introduce and describe the topic in deep. And the second talk will be end-to-end management in integrated TN and NTN networks using system-level simulations and testbed. This will be presented by Sahana and Mustafa from Fraunhofer Erl in Germany. So the two topics are quite correlated, so I'm very happy that we have this opportunity here. So each presentation will last 20 minutes, and people that have they like to have a question, they can pose the question after this presentation. If you like, you can write in the chat, and I will pose the question myself. That is also a good option. Okay, so now I'm stopping my presentation, and I give the floor to the presenter, to Greg and Tarun. They will give their presentation now. Thank you. Thank you for your attention.
Greg, please go ahead.
Okay, thank you very much. So my name is Greg Skidmore. I'm the Director of Propagation and our wireless tools for wireless communications and for radars and sensing at Remcom. I've been with Remcom about 16 years, and my background is in electrical engineering. But Remcom as a company is very focused on modeling and simulation of electromagnetics, of propagation, of just anything that involves signals propagating or antennas radiating, anything related to electromagnetics. I'm going to be giving a presentation on some work that we did with NB-IoT, and then after that, Tarun is going to show some things. Tarun, would you like to introduce yourself before I get started?
Indeed, pleasure. Thank you, Greg. Electrical engineer myself. I've been at Remcom for almost at the same time as Greg, about 16 years, and immense pleasure to be a part of the IEEE Future Networks. A couple of months ago, we gave a talk on comms and sensing, integrated communications and sensing. Very broadly, Remcom is in the base effort of the physical layer, developing the channel models for communications and for sensing, and also looking at near field effects of devices with PCB and down to the circuit level. So from circuit down to the channel, and reciprocating the whole RF system and digitizing that. That's really our focus and what we work towards. Thank you, Greg.
Okay, so let me go ahead and get started. So today we're going to be going over a talk on simulating the use of LEO satellites to extend narrowband IoT coverage in rural areas. So what I'm going to be talking about is the use of ray tracing in modeling and simulation. What we're going to be going through here is basically an example, but what we're hoping to show is that modeling and simulation can be used for NTN for a variety of applications and for doing trade-offs, looking at terrestrial coverage versus NTN together. So this is one example, but hopefully it'll give you an idea of some of the kinds of things that we think we can do with our tools and the way that we're approaching this problem. So the general problem of extending NTN, basically satellites and high-altitude platforms, obviously in this group, this is a big part of 5G. We've got, when we went to look at this study, we were trying to look at some of the advantages and the challenges with LEO. The fact that it could do wide area coverage, offer long-term reliability. Some of the things we want to look at is how it could help augment terrestrial infrastructure to give us IoT coverage over a larger area in rural areas where there may not be great coverage from the local cell towers. So we set up a problem to look at this, and we're going to basically be showing that example here today. So the key requirements then for M2M or IoT are low power consumption, reliable connectivity, low data rates are acceptable. So this can be solved with a narrow bandwidth, low power WAN kind of solution like narrowband IoT. So in this example, we chose narrowband IoT as our example. This is obviously something that's been getting developed through the different 3GPP releases, including 17, 18, basically to be incorporated from LTE into the 5G ecosystem. So we were looking at how this could be used and putting together this example to see how it might benefit for IoT. We looked at uplink and downlink, basically looking at data rates of up to 250 kilobits per second max. So some of the big obvious advantages here are that the constellations of LEO satellites can offer wide service coverage. They can cover things that may not be easily accessible from urban or suburban areas that are nearby when we get out into areas that have lower coverage from the terrestrial systems. So the low Earth orbits give us low latency relative to at least other satellite solutions, and latency down to around 10 milliseconds or less when it's directly overhead. Obviously, this will vary on where the satellite is and the elevation angle. Lower path loss as well, again, compared to other satellite solutions, given the lower distances. Still fairly significant, but at S-band, maybe around 160 dB path loss. Now, some of the challenges are the Doppler shift with the low Earth orbit satellites. Because we're lower, it's the higher velocities. We can see Doppler shifts of plus or minus 40 kilohertz. And when we're looking at a total bandwidth for NB-IoT that's only on the order of a few hundred kilohertz, this can be substantial. So compensation needs to be applied. We didn't directly simulate that compensation, but in the paper that this work is derived from, we did talk about this and do some calculations and look at some of the impacts that this could have if not compensated for. Other challenges, at lower elevations, the latency could increase. Obviously, as the path length's getting longer, path loss can increase due to the longer path lengths, refraction effects, potentially atmospheric absorption. Atmospheric absorption, though, wasn't too bad at the S-band, so this is a fairly good example that we're running through, a good application. Another thing is we get lower the terrain shadowing, and you'll see in this example that we put in trees, so penetration losses from the foliage also can be worse as we get down to lower elevation angles. Other things that could be important, ionospheric scintillation can cause time-dependent fades. We can also see things with depolarization, Faraday effects, and other things. So all of these things are things that we have a prototype model that we brought in that we were looking at. But the main things that we focused on for this study were really just the refraction and the apparent angles due to that refraction and the atmospheric absorption. And then folded that in with our ray tracing, which includes multipath shadowing and other effects from terrain, buildings, etc. So looking at the Doppler shift, though, we did do some calculations. This shows Doppler shifts as our elevations are changing from 25 degrees to 155 degrees as the satellite is moving overhead. Shows, first of all, how much we can see in kind of our worst cases, plus or minus 40 kilohertz of shift, and also the rate that it's changing as the satellite is in motion overhead. So not just the compensation that's required, but how that compensation needs to shift with time. So to study this, we brought in Wireless InSite, a product that we have that has 3D and 2D ray tracing models. It has a suite of different models for communications and post-processing as well. So being able to take ray tracing, look at receive power, compute signal-to-noise ratios, or signal-to-interference plus noise ratios, and then move into throughput estimates. All of these things are captured in the tool. We've got MIMO capabilities here as well, although for this we were focused on mainly individual antennas. And with the MIMO, we can do beamforming multiplexing. We can go up to millimeter waves. So a lot of capabilities here. Millimeter waves aren't too important, or not millimeter waves. The diffuse scattering and the other effects at millimeter waves wouldn't be too important down at S-band. But these things are here when we look at other frequency bands and start considering other possible applications. So the applications typically 5G or 6G coverage, dense urban areas like we see at the top left, indoor Wi-Fi, long-range rugged terrain, and even some work we're doing with NASA looking at propagation in lunar environments as well. Satellites can come into play there too. So a lot of different things that we can cover. In this case, we were basically using the ray tracing with urban and suburban, bringing that into the rural areas, and then combining with that satellite overlays to see how we could improve our coverage by bringing in LEO satellites. So when we're looking at satellite propagation, there are a couple of ways we can do this. One is to have a plane wave coming in from above. And this example that I'm showing here is actually using a plane wave. Another possibility is to actually place a transmitting or receiving source at a particular point, which is what we actually did for the LEO satellites in this study. But what this animation shows us is when we're using ray tracing, we can see paths going through trees, interacting with buildings, and obviously coming in for very high elevation angles for whether we're looking at GPS or NTN. So this shows you the kinds of things that we can see, and you can see a little bit of shifts that are happening as in this case, we have a person moving down a trail through the park, and you can see the multipath is shifting and moving and changing as the person is moving through this scene. And you'd expect possibly even more rapid changes if they were moving down a street between buildings. So this is the kind of thing that ray tracing can give us insight into when we're looking at applications like NTN. On top of this, for this study, we also brought in an R&D model that we have that's not yet released, but it has some additional capabilities specifically for satellite to ground paths. So this was something that we augmented our ray tracing with in calculations looking at atmospheric refraction. So we could see what the apparent position of the satellite would be based on refraction through the atmosphere. The atmospheric absorption. Typical models in terrestrial applications are looking at absorption on the surface. Once you start looking at satellite applications, we need to think about how the atmosphere is changing with elevation. So we developed a model for this as well that can include standard atmospheres or can take in atmospheric refractivity data. And so that can give us estimates of atmospheric absorption as we go up in elevation on our way to or from the satellite and capture those effects. We also have ionospheric scintillation, depolarization, weather attenuation for things like rain, clouds, and fog, and other effects that come into play when we start getting at low elevations where we see beam spreading due to the refraction and multipath fading effects. So in this study, the main things that were of key importance were the bending of the paths from the refraction and some of the atmospheric absorption effects. And I just say minor here because down at S-band, they're not too severe. They can get more severe as we go up to higher frequencies, but they did have effects on the path loss as well. So looking at our scenario, we set up a ray tracing simulation with a large rural area, rugged terrain here with some hills, rises, valleys, and some trees. So nothing too large, no major hills or mountains, but some rugged terrain where you could see some loss down into the small little dells and other things between the hills. We have a suburban area over here and an urban area on the left, a couple of base stations this is basically like the edge of a city on the left side. And on the right side, we have a small suburban area that's got a base station as well. In this simulation, we didn't include any base stations between, so the coverage, it's over about 20-kilometer range. The coverage would be from these base stations, or we would need to fill it in with something else, and that's where the satellites come in. So here we see the urban base stations, the suburban base station, and then the coverage area was laid out as a coverage grid to calculate and simulate things like the receive power and then the signal to noise ratios over entire grid between these two, between the two areas, the urban and the suburban. So for the 5G base station, we had EIRP. I think this is actually reversed. We had an EIRP around 40 dB MI. For the satellite, we had a very high EIRP between the assumed gain pattern and the transmit power. That was 66. Our IoT receivers are much lower power, about 23 dBm power and fairly omnidirectional antennas. And the noise figures also varied. The base station and satellite with very low noise figures, IoT systems assumed to not be quite as good at handling noise. Terrestrial noise was assumed to be higher than up at the satellites. And then with this, we used ray tracing to predict multipath. This is just an example image of some multipath coming down from a satellite, combined with some interactions that are going back and forth with the urban areas. And this is an example of the kind of multipath we might see to one point in this coverage grid. You can imagine this repeated over this entire scene, point by point, and then combined with additional multipath of all the potential propagation paths coming from the urban area and the suburban area to fill in the coverage over this large scene. So starting with coverage from the terrestrial network, if we just do narrowband IoT, but use the terrestrial network, the two base stations, looking at downlink and uplink, we can see very high coverage, very high SNR levels, especially in the suburban and urban areas, and then they fall off as we get between. Everything we see in these coverage maps where we see white is where the signal levels have now dropped below the noise floor, possibly because there was a small ridge, a small little dell. or ravine or some other area where there wasn't good coverage. So throughout these areas, we see quite a lot of white. So while there are some areas that are getting good coverage, there's certainly a lot of places where there would be strong dropouts. So then we brought in the satellites and did the simulations with ray tracing, augmented with the R&D satellite model that I mentioned. The results here show at a series of different elevations for our LEO satellite, 25 degrees, 90 degrees overhead, and down to basically 25 degrees on the other end. And we can see that from the satellites alone, this is without the infrastructure, we're getting, at the low elevations, we're down close to the noise floor, down around 2 to 4 dB SNR. Once we get overhead, we're much better off. We're up higher around 10 to 12 dB signal to noise ratio. But one important thing is over most of the area across these angles, especially at the higher ones, we're getting something above the noise floor, which is different than what we saw with the terrestrial. So we can see that already if we bring this in, we should be able to get at least a low level of signal coverage as the satellite's passing over. We see something similar but a little bit higher for the uplink, and the reason it's a little bit stronger is the combination of better noise figures, just in the assumptions on the noise levels up in vacuum compared to down on the surface, and a few other things. The uplink ended up doing a little bit better in this scenario, despite the lower power of the IoT transmitter. And so overall, we see coverage here pretty much across almost every point we're above the noise floor in this case, and in some cases quite fairly substantially, up around 13 dB maybe at the peak when we're directly overhead. So for the NB-IoT, something over 10 dB SNR is easily enough to get the higher levels of data rates up around a couple hundred kilohertz. So when we look at a CDF of the SNR levels, you can see the CDF in black is from the terrestrial network, so it's very spread out. When we look at the noise floor, 0 dB SNR, you can see that we're almost 70% of the region that we were looking at for downlink was at or below the noise floor, and almost 60% for the uplink. And the rest of these lines show what the satellite coverage can bring in, and shows that for most of these angles for downlink, and for pretty much all of them for uplink, we're above the noise floor, or at least mostly above the noise floor, except for a few points for all of these angles. So now when we look at the comparison, this is again the terrestrial base stations, but this time looking at an estimate of throughput. So we built up throughput tables based on signal to noise ratio for NB-IoT. These throughput tables go up to a maximum of about 250 kilobits per second due to these narrow bandwidths, and they're also limited to QPSK, so fairly low modulation encoding schemes. And this is showing the estimates of throughput across the area for downlink when we just had the terrestrial, and again we see lots of areas with dropout. When we fold in the satellites, most of the area is now covered, and for uplink, pretty much all of the area is well covered, and we're able to get for uplink, we're able to get above, for most of it, we're able to get above 200 kilobits per second. For downlink, looks like we're pretty much able to stay in the 1 to 200 kilobit per second range. So for a simple IoT application that doesn't need very much bandwidth, we've got good coverage when we bring in the LEO satellite. So the study demonstrates how we can use simulations. This conclusion slide talks about the conclusions really from the study, that the LEO satellites definitely improved the throughput and the SNR coverage. The overall conclusion really here, though, is that for other applications, whether we're talking about NB-IoT or something else, this gives us an idea, I think, of the kinds of things that we can do with simulations. Ray tracing gives us an ability to do detailed multipath, which can become extremely useful, especially in urban areas, but can also be used in rural areas. And we can then put that together with the satellite links to look at the two together and see the combined coverage for this kind of a simulation. So our goal here was really to show how ray tracing and propagation simulation can come in and be used in this kind of a manner to do cost-benefit trade-offs and to see improvements for things like NTN for IoT. Okay, and with that, I'll turn it over to Tarun. Some of our future work that we're looking at, we're expanding. We've got some prototype capabilities we're looking into, and I think Tarun has some things that he'd like to go ahead and show. So please show us, Tarun.
I'll keep it very brief and then, of course, hand it over to our friends at Fraunhofer. So I will share my screen briefly and show some of the work that we're doing with folks in the CNR, the Council for National Research, and the Italian government. For example, Alberto Gatta, who is a part of the Future Networks Committee. Some of the latest work that they have been doing in collaboration with us is this leveraging AI paper with developing UAV aware channel models based on geometry, based on the sites that may be dependent on urban versus suburban versus less dense urban. And this is one of the latest works that was published explaining the models comparing to 3GPP for various types of urban and geometrical models. This is built off of the previous work that was done in PISA with Chianera again of SNR-aware route planning for UAVs and NTN communications. So based on this and based on the type of collaboration we do with various research institutes, including Fraunhofer and HHI and on other locations, we're building prototypes of new software that will help researchers look at analysis of communication links in various non-terrestrial types of environments. And this is one of the examples here of a moving transmitter at the ground level in Tokyo, for example, and in this case, actually San Francisco. The moving location is actually over here. This is actually moving transmitter, receiver on the ground while the transmitters are static in space. This is a 30-second simulation showing satellite connectivity to ground. This is a concept that we worked on earlier, and that has been built up into looking at moving satellites over a 1 hour or longer period with motion specified of those. And these trajectories are actually live location places based in time of LEO satellites that we're looking to develop. So if you're looking to partner and extend these types of ray tracing techniques, which are proven and scalable for large-scale scenarios, including the effects of multipath in urban areas with terrain effects, ground bounds, etc., and we'll be happy to talk to you about this further. Thank you, Greg. Thank you, Giovanni. Thank you, the IEEE Future Networks. It's our pleasure.
Thank you. Thank you very much for your interesting presentation. We really enjoy all the detail. I think we have some question in the chat. One concern the simulator. So which simulator environment you use, and if it is possible to reproduce a real-world experiment. So probably your slides in part cover this.
In the end, yeah. I think Akram's question is basically about, modeling real positions of SpaceX LEO satellites and a 5G smartphone on the ground. That's exactly what the last iteration was showing. Those are 4 satellites over a 1 hour period connected to an antenna on the ground, static. Our goal is to build both of those in motion. Of course, the satellites over a longer period, like 24 hours, connected to mobile networks on the ground.
Great. So there is another participant that has raised at the hand. I cannot see well because there are so many participants.
I'm
please,
here.
Please.
So
Thank you so much.
I want to know what kind of software you use for the simulation. Is it all GPU based, NVIDIA GPU based, or do you use any other Arcom, or what is that? And
these are in-house.
Is it open source? Where can we get if we want to do something of this kind?
Yeah, we're a software vendor and develop these physics models in-house. We're actually a DoD contractor for the U.S. government that develops these solutions for the Naval Research Lab, for the Air Force, and others. Some of them we actually have commercialized and support through active development. Wireless InSite is one of those. gold standards for ray tracing that is being used. And it's very different than likes like Shiona, which is based on differential ray tracing. This is actually shooting and bouncing ray and image theory technique, which is very different in terms of ray tracing. In fact, no ray tracer is alike. So the term ray tracing is in a very commonly used method, but each method is very different.
I've used at AT&T this, I wanted to check, are there any significant changes to the urban and the rural and the various modeling we do from the older generation tool to this new ray tracing generation tools?
Indeed, the multipath is one aspect, is the effects of map-based modeling. So specific sites, validation, etc., is a critical piece that is now moving out of, say, generic stochastic models that can, measurement in one city applied to another, and the deltas of, say, 7-10 dB RMSE over path loss has been reduced to now very, very refined, say, 2 dB to 4 dB. So the measurements that are performed in these sites has been now cross-validated, and then those models are now not required.
But these are applicable only to the GPS, which is followed by US.
It can be
not
GNSS,
necessarily
it
by
can be
other,
L1, L5. These are frequency domain techniques, and actually any bandwidth, any frequencies, and any specific transmit receive heights can be modeled. So we're actually modeling this with NASA for orbital communications on the moon. The same ray tracer that's used for terrestrial, but the physics is slightly different with terrain interactions, roughness, of course, no atmosphere, but those are simply add-ons to the model that can be adjusted. But the base ray tracer, the physics-based ray tracer, is the same.
So you mean to say that we can adjust if it is a what do you call Tropic of Cancer, Tropic of Capricorn, or towards the equator or towards the pole, and we can adjust
the refraction angles across the atmosphere would be handled based
most
on
of it
the
in
elevation.
LEO is in the equatorial, right?
We can extend this conversation, I think, on a
Sorry,
offline.
time is
Thank you.
We have many questions in the chat, and time is short, so we have 1 minute, about 1 minute before they hand over to the second talk. And then I don't know, there are some, I don't know if you see the chat.
Yes, Leo versus Geo. Yep, absolutely, this can be applied. There's no concern.
Yes, you can go through for one asking foliage effect, other what is the impact of a Doppler, another is a satellite the assumption of the satellite antenna, the eye rate you show is like a single user. So if you can have some final comment.
Please, Greg.
Yeah, I saw some of those questions. So the one on foliage, so the angle is taken into account because the ray tracing is doing a penetration loss model. So it's if it's penetrating through trees, there'll be loss. So if something's close to a tree, it will probably still get loss even at slightly higher elevation angles. But what will tend to happen is once you get at a higher elevation, you'll shoot by the trees and you won't suffer that loss. So it's all very geometric. It's based on how you define the scene, and if you saw in that earlier image, there were small areas of foliage that were dotting that landscape, and that's where the attenuation was coming from. So the higher angles avoid that simply by not having to go through trees. And that was the loss was being applied using something called the Weisberger loss model. Some of the other questions, I think, Leo versus Geo. So latency would obviously, our estimations on things like throughput are not taking that latency into account, but obviously there would be effects there to be considered in a study. If we went to Geo, we'd probably be coming in with a plane wave because of the greater distances. There are things that we can take offline and talk about more as well about the satellite model, because there is a little bit of some of the things I talked about are the prototype model that we have. Some are the things in the ray tracer. So can certainly do follow-ups on that, but there's just a lot in the chat window. I probably should kind of leave it there unless there's some specific questions you want me to address, just to make sure you can get to the next speakers.
Yes, maybe you can answer via chat to the other question during the talk if you like. So
Okay.
as you present. Okay, so now
Okay.
we have to move to the second talk, and this is presented by. Okay, let me recover. This will be endowment management in integrated NTN and network using system-level simulation testbed. Presented Sahana Raghunandan Mustafa Roshdi, and sorry for the floor is yours. So Sahana and
Yes.
yes.
So you can hear me, right? Thank you very much, Vani. Yes.
Yeah.
Okay. Thank you very much, and good afternoon or morning, good evening to everybody here. I'll just make a short introduction of ourselves. I'm Sahana. I work as head of broadband and broadcast department in Fraunhofer IAS. I've been working in the satellite industry prior to my current work here at Fraunhofer. We focus on a lot of activities related to terrestrial and non-terrestrial networks with a special focus on 3GPP-based simulations and testbeds. So happy to be here to actually give this presentation. I'll hand it over to Mustafa very briefly to also introduce himself, and then we'll start the presentation. Yeah.
Yes. Hi, everybody. I'm Mustafa Roshdi, and I'm with Fraunhofer IS as a senior engineer, I think now for 7+ years. And my focus is on network level simulations, mobile network level simulated developments, whether on the system level or the link level. And also right now, I'm very active in the field of how can we integrate AI for network optimization, so to use AI for RAN optimization. So I'm glad also to be here for the invitation from the IEEE Future Networks, and I'll hand back to Sana.
Okay, thank you. Okay, so what we've been working in the department and also focusing on a lot of different types of simulation environments and test beds. And our latest work actually showcases and addresses handover management in assuming integrated TN and NTN networks. Can you still hear me? Okay. All right. So what is the motivation for this? So going into from 5G to 6G, it's of course known that NTN is going to be an integral part of the entire ecosystem of services. So you could have spaceborne, airborne, ground-based platforms, and the complexity of the 6G networks, especially with the larger number of services and use cases that are also being addressed in 3GPP SA. Also highlights that it's going to be challenging not only from being able to manage the infrastructure, but given the different options of routing packets and understanding different link conditions, there's going to be a huge effort required to address how can we handle integrated systems, how can we ensure that the handover can be managed appropriately. So of course, there were fundamental differences in the physical propagation environment between TN and NTN, specifically related to velocity, dual mobility, and propagation delay. Which means that in an integrated systems, you have to keep in mind that the earlier 3GPP releases, which addressed mostly terrestrial requirements, had to be modified. And of course, going forward, we have also the introduction of AI ML for mobility management, also to be able to address the very core issue of the frequency of handovers and also to make sure that the service interruptions are minimized. So of course, some of these are traditional handover management issues, but it makes it all the more complex given the integration of non-terrestrial networks and the protocol stack with certain quality of service assignments. So what has been the standards-driven solutions? 3GPP specifications has introduced additional conditional handover events, which is based on measurement, location, timing advance, and elevation angles. There's also, of course, an introduction of multi-radio dual connectivity and interface specifications such as XN, F1, or NR based on the type of satellite payload architecture. With all this, the latest AI-aided predictive analytics are also being discussed currently within 3GPP, but also within ORAN, which can make use of like the temporal, spatial, and the spectral features to be able to ensure that you have a smooth handover when using integrated infrastructure. So what we've done in the work that we've presented currently, which was also presented in the international workshop on smart antennas a month ago, was to address two types of AI-based prediction analytics. One was introduced, one was looking into the 3D network simulator that Mustafa will talk about, and the other one was based on ORAN-based testbed. In both these cases, the goal was basically to address handover management, but with in first case to minimize the number of handovers in a hybrid network based on the physical layer metric measurement. So where we know the SINR, we have AI models that are trained offline, also based on UE mobility patterns in order to initiate early handover. The second one, which is based on the ORAN-based testbed, which I will introduce currently, was basically done to expand the handover optimization to an ORAN-based implementation. So for this, we also included models that were trained offline, but we were also able to address transferability where the offline trained models were also basically deployed within the testbed and was used to predict the resource block usage. And the advantage of doing so is that when we address MAC layer throughput or MAC layer resource block, it automatically has to consider the impact of both the physical layer, that is the SINR variations, and also the application level requirements. Since the resource block assignment directly is a product of the scheduler, factoring both the higher layer and the lower layer metrics. So let's take a look at the test beds that we integrated and set up for this purpose. The one thing that was a bit of a challenge for us is to understand and figure out the state of the art in terms of test beds, not only in terms of understanding and setting up the interfaces between the different components as you see it here, but also to ensure that we have the latest set of features especially with respect to 3GPP as well as ORAN, so that we can actually deploy the XApps that are used for optimizing the handover. So for this, as you see, for quality of service, we have two types of XApps, which actually one which monitor, so monitoring XApp, and a XApp meant for predicting the quality of service. So what was set up here were two nodes, two G node Bs, which was also connected to a UE SIM box. And this essentially was also used to be able to integrate different types of channel conditions where we could also tweak the physical layer, say impairments that would be then measured by the scheduler. So as I was mentioning before, we have two types of XApps that influences the handover decision. And in order to be able to address this, we had data that was actually collected, a public data set that was actually used to train a rather simple neural network, because here in the testbed, the focus was on the temporal features. So we had bunch of synthetic traffic traces, which could give us an understanding of how traffic prediction could potentially influence PRB utilization. And we use this trained neural network to be deployed within our testbed. And this neural network, of course, was also trained on different types of features that are evident in different types of traffic traces. And the LSTM model that we chose was particularly chosen to be able to do a certain type of optimization in terms of forecasting. So what we did find, which is also intuitive, is to understand how the prediction performance actually degrades when you have a larger time horizon window. And we also did some tests and calibrations to understand what should be the time horizon and for how long should the prediction, or how accurate will the prediction be based on the future time steps. So the general trend is actually captured in the traces that you see here. But in general, of course, the model struggles to predict the peaks or sudden changes in the data when you have expanded time frames. So the first figure compared to the second figure actually shows that if we want accurate prediction, you really need a large set of traces, but also you need to operate on a much lower time horizon windows, which is in line with the ORAN RIC and the non-real-time RIC operations in terms of the accuracy in which that control loops have to work. So this is one of the captures we have from the ORAN-based testbed. So it's a single snapshot where we have a large number. We have quite a few UEs that are connected to the network. And what we see here is without the real-time intelligent controller, that is without invoking the XApp, as the number of connected UEs increase in the network, there is of course a drop in the average throughput because we do not have, because of handover conditions. So which means that we have the normalized PRB utilization maxes out. So with one G node B active and no handover initiated, you can see automatically there's a drop in the average throughput. For all these tests, of course, we did make an assumption about the overall bandwidth that is available based on the estimated number of UEs that would be connected to the G node B. And what you see with the RIC is that we have two G node Bs as shown in the testbed setup, and by enabling handover to a G node B, which has less load, we're actually able to prevent a drop in the average throughput observed at the network level. So what is also seen here, this is a quick video. So this is a quick video of the demonstration that we set up where the UE SymBox is starting. We see the successful synchronization of the UE. You see different active UEs in the network. And then we have the XApp. So we have the monitoring XApp that is activated. And then we have the observations done over a rolling time window. You see the load, we see the average throughput, and we see the number of connected UEs. And we were also able to showcase like what happens when you start now the predictive quality of service. So now we have the actual control loop with the decision making activated with the help of the monitoring and the predictive XApp. And you see now what I showcased as a snapshot in the previous slide, where you can look at how a trigger of an handover from which enables the UE to move from the active G node B to the G node B, which is more idle, actually enables showcasing that there is possibility to maintain a certain average throughput in the network in this case. So this is what we have demonstrated, and at conclusion, we can talk about what is to come next. With that, I hand over to Mustafa. I think we can stop the demonstration here. And yeah, okay, over to you, Mustafa.
Thank you, Sana. So now I will move forward to the second part, or one other part of our activities in this field, which is not directly going to test beds, but taking a step back and trying to simulate networks or such complex network on a much larger scale. So please go to the next slide. So and for that purpose, we are working on developing our own system, 3D network system simulation, which aims to simulate complex TN and TN integrated networks with terrestrial coverage and non-terrestrial coverage represented in multiple types of nodes, whether they are high-altitude platforms or LEO or the MEO or the GEO satellites. And so on the right-hand side here, you see the the architecture, or a simple architecture of a view of the architecture of this simulator. And so we focus here on the full protocol stack of the user plane data. And in that case, we have like an abstract implementation of all the RAN protocol stack layers that is based on a well-known well-known library in the realm of Omnet++, discrete event simulator that's called SIMO 5G. So we start with this as a baseline, and we have extended this quite extensively with NTN mobility, with multiple now we can model airborne GNODBs with the flight path either defined in NORAD TLE format or specific trajectories. We can also have ground users that follow either static or vehicular mobility models using the well-known simulator of urban mobility tool, SUMO. And we also have more complex antenna coverage models for both the ground and the flying nodes. We also have integrated channel models for TN links as defined by 3GPP and 38901 technical specification. And also for the NTN links, we have implemented modeling for large-scale, for free space path loss and shadowing and cluster loss components, as in technical specification 38811, as well as the IT recommendations for atmospheric and scintillation losses. And for this is then we use this this simulator. One aspect of it, we use it also to explore complex issues such as the handover, generate data to try to train AI models on and integrate them natively into the simulated environment to be able to test whether they can help us solve the problem or not. So for that case, we have also our own AI engine that allows us to train models, as you can see in the bottom figure, and then compile them. So train them in Python using well-known tools and libraries, and then compile them and then link them to existing modules within the simulator. These can be prediction models or reinforcement learning models, and they can interact with the simulator in multiple ways in an online manner. Please go to the next slide. Okay, so I will go quickly over the existing handover or the legacy handover, which is I can say that it's similar to the conditional handover in 3GPP as defined by 3GPP, but not exactly one-to-one. So the legacy handover process, which is implemented on the baseline in SIMO 5G. So this basically all the UEs receive periodic measurement messages to calculate the RSSIs from each of the GNODBs. And once the UE will then do these measurements, and then once it measures that the RSSI from a specific candidate GNODB is higher than the master GNODB with a specific delta, then it will send these measurements to the XN manager, which will then trigger the handover from the master GNODB to the candidate GNODB. So of course, when you have then dual mobility, when both the UE and the GNODB are moving, and also there is also the delays in the link, so these measurements might not be actual, might not be recent, and therefore in that case you might, once the decision is made, it might already be too late because the situation in the channel has changed, and therefore it will not be valid. Next slide, please. And this is where we introduced an improved AI-assisted handover, which is based, instead of replacing these instantaneous measures and then and being the trigger of the handover process, is to actually do a prediction of what the link quality would be in a specific scenario over a specific prediction window for all of the GNODBs, and then make the decision based on that. So instead of being dependent on the actual current measurements that the UE reports, we should predict in the future and allow for early handover procedure, given our awareness of the mobility of each of the nodes and the situation in the scenario that we are simulating. And that's exactly what we did. If you move to the next slide. Okay, so this is our simulation scenario, which comprises of one, so it takes place into the southern city of Germany, Rosenheim, which is a city in southern Germany. And we had an automotive test bed in that city, so we know exactly the placement of the terrestrial base station in that region. So we place one of these terrestrial base stations in the city of Rosenheim on top of the Deutsche Telekom building. We generated traces of more than 800 vehicles that are driving in this region. We then simulated, we tried at the first step to simplify the problem. So we simulated a high altitude platform as an NTN having a generative payload, so acting a full GNOB in the sky. And these high altitude platforms then will be circling the region. And the question is, when should the vehicles, as they move inside this region, do they hand over from one base station to the other? And so for that, we generated the data offline. We trained the prediction models for each of the TN and the NTN GNOB. And then we saw these validation of these offline training in the next slide. First, for the TN base station. So in the first column of figures, you can see these are the actual data collected for the traces of the vehicles inside the region of interest. So this we can only here see the streets of the simulation area, where we collected all the data from all the moving vehicles, and the terrestrial base station is placed on the left-hand side of that region. So this is the actual data. The middle column is the prediction of the model, the trained model, and then the error of the prediction. So because of the nature of this model in the terrestrial realm, so we have a stochastic model that does not deterministically determine whether there is a line of sight component or not. So this has some additional variation that the model cannot predict accurately, but despite that, on average, the prediction error remains quite low. And the next slide, we see the results from the prediction from the NTN model. In that case, it's a high altitude platform with a very wide beam that is around 24 kilometers. So in diameter, and then the variations actually within the simulation area, which is around 2 square kilometers, were quite low, and therefore the error in the prediction is quite low as well. So, and in the next slide, we can see the online results of the validation of these models. So on the left-hand side, you see in the video, the vehicle starting driving close to the terrestrial base station, and there is the high altitude platform circling the area. And then with the online training model there, the handover decision only happens once, when the vehicle actually starts to make sense for the future that the vehicle should move to the non-terrestrial node. And we see on the right-hand side that when we use this legacy handover procedure, we had actually more than around 11 handover events during this same exact path of driving, while we only had one handover event with the AI-assisted handover, and that resulted in a better overall SINR when we follow. Of course, as well, would also result in better throughput because you don't have to do handover back and forth between the TN and NTN. Okay, and with that, I will go back to Sahana.
Okay, thank you, Mustafa. So what we have, of course, with the two components of our work, we were able to actually showcase how a simulation environment and test beds can be set up to be able to evaluate different types of handover optimization schemes with some type of a predictive analytics built into it, either based on a combination of physical layer metrics such as SINR in combination with the influence of the traffic. Of course, there's room for a lot of work to be done, especially with respect to including multi-orbit constellations, enhancing the simulation environment with specific type of satellite antenna models, including backhaul link, and also showcasing in the future different types of like agentic AI, whether it is for dynamic resource or beam management. Another step that we are doing, and also across multiple projects, is to enhance our testbed capability itself, to be actually able to showcase a good integrated TN NTN handover mechanism. It's also fundamentally necessary to have a testbed that's capable of different types of functionalities, including the latest proposed 3GPP features, and also being able to establish some level of consistency and interoperability between simulation and testbed environments. With that in mind, I want to end the presentation with one of the ongoing testbed activities called 6G Lino, which is also funded by the European Space Agencies, where we are actually going to be developing an in-orbit laboratory, which is specifically also capable of showcasing the use case of handover scenarios. And the idea would be in the future to really have such a testbed also integrated with some AI-based techniques to showcase handover optimization for integrated TN and TN scenarios. So with that, I think, thank you very much. That brings us to the end of our presentation.
Thank you so much for this very interesting presentation. I really enjoyed it, and I think we are a little bit out of time, but we can guarantee for sure time for question. Is there any question from the
Prakash here? I'm
Prakash,
asking
please.
question related to the what do you call the free space, and how do you correlate the free space in the air or in the atmosphere versus you do in the terrestrial network? And then, are you going to use the same TETM, which is the transverse electric and transfer magnetic, or you are going to look at what you call the circular polarization, etc., in satellite? How do you really help in that respect in the layer 2 when there is so much of a difference? And are there anything that we need to know, understand this better?
To know are you talking in general about simulations? I mean, from our side, we have these are all based on 3GPP channel models, right? So we are closely observing and have contributed to the non-terrestrial network evolution and the standardization, where we also know that we have some of the calibration results as references to understand what the CDF curve of different, of SINR under different types of path loss and propagation loss. So this is something that is established as a baseline prior to actually showcasing the work both for the terrestrial and the non-terrestrial case.
So it means you will continue with the FR3 right now and not any other frequencies, and single carrier mostly. And
there is no limitation in our setup with respect to the frequency range. So we've kind of showcased it for a specific scenario, but since for both the simulation, at least in the simulation world, it's agnostic, but in the test beds, of course, we're dependent on the features and the components that are available. But Mustafa, if you want to add.
The channel models, I think, so if I understood the question correctly, so that the channel models that we have at the moment are for FR1 and FR2, at least the ones that we're using in the simulation. So the FR1 and FR3, and we do not have channel models for the millimeter waves at the moment. So so we are limited to FR1 and FR3, at least in terms of simulation, the validity of the channel models that we're using.
And the last time I heard was multi-antenna, array antennas, which you had presented, probably Australia. Something to do with the ability to use those to generate the different frequencies in the different ranges. And the other part is always a limitation on the, what you call the amplifiers, low noise amplifiers, LNAs or whatever they call it.
So at least on the simulation part, we have an abstract, at least the channel models are empirical channel models. We don't have the details of the physical layer they're implemented. So these are empirical channel models that we are then used to calculate specific path loss and link budget values that we are then used to evaluate what the SNR value. That's at least what at the end it matters to us. So on a system level, simulation level. That to be able to depending on the positions of the two nodes, what would the link budget be, and what would the empirical channel models, the evaluation that would result in a final value for an SINR for a specific resource block allocation. So, but more than that, on a system level, the physical layer is the rest is an abstraction. So we have our own error models that based on this SNR we can determine whether a packet is received in error. But the rest is abstracted in the simulation.
Correct. The physical implementation will be a big challenge. I don't know what we are going to do
Yeah,
there.
so
That's a big question.
just on the testbed side, yes, we have actually showcased a lot of live transmissions over the satellite, including the front end. So we do have a team that actually focuses on the antenna solutions as well. So I don't know if you were referencing that, but in the context of handover management, this is it is a challenge, but this is also why we built out also a testbed infrastructure to actually test out how it would work in reality with an emulated protocol stack.
Sure. So you are getting the players like Huawei and
Maybe
Sorry, we
all those
maybe can take other
do a
take other
potential
question,
testing.
and
yes.
you can continue maybe offline. If there is, I don't know, Prakash, I would like to, because the discussion is interesting, but just to give remaining time to other participants, if there are other questions from the group. Yeah, you are, you are booked. You are booked. There are some, okay, great presentation in the chat. So people asking about the mobility in using NTN. I don't know if this question is really relevant or is maybe less important.
Yes, I mean, I think with at least with mobility, I think maybe Mustafa can also add to it. We have two different types of environments. One in which the test bed, the first one where we actually can integrate a channel emulator with different types of mobility patterns, but Mustafa can add to the simulation
For the
aspects.
simulation, so for the NTN, so we can at least for different types of nodes. So for the satellites, we can either do TLE based mobility patterns or also trajectory based mobility. So we start at a specific point in space at a specific altitude, and then we specify the trajectory, and then the satellites will follow that trajectory. Also, we can for the high altitude platforms or the UAVs, we do either linear mobility or circular mobility patterns. So we have multiple ways to model the mobility in the simulator.
And one quick question on my side, because we are involved in two European projects dealing exactly with the mobility between terrestrial and non-terrestrial. So we are very interested to vertical endover, and so we really appreciate some useful detail. I'm wondering if you have take into account, I suppose for sure, yes, latency in the endover performance. If you have some, the impact of it.
So at least in the context of the test bed, especially with the timers and the control plane involved, this is a very good question. We haven't characterized it completely. However, I think Mustafa can also comment on it. We have done exercises to abstract, actually measure the latency within the simulation environment. So maybe Mustafa can add to that.
So we have done multiple. So for the terrestrial network, we have collected a lot of data from our testbed to really enhance our latency models within the system level simulation, because that was something that was lacking from the baseline that we're using. And for that, we have enhanced like the processing latency. And since we're also focusing on, or at least we are still simulating on the user plane, the control plane latency was missing. And for that, we needed to develop our own latency models. So with that, we have done a lot of work on trying to enhance these latency models within the simulation. I wouldn't say that we are one-to-one compliant to what the standard has, but we are trying to be as close as possible.
Okay, great. We hope to see you maybe another occasion, because we have a topic in our research that is very close. So we
Absolutely. Yes.
can happy to exchange some good ideas. So
Absolutely.
we have another.
Thank you.
Thank you so much. We have another question from Prakash, and then Prakash, now we can conclude with your question, because I saw the hand raised, if I'm not mistaken, or maybe not. Prakash, you finish, or you have other question? Or in case there are any other question from the participant, because we have so many participants, the peak arrived to 92. So I think
Information clock SIB. So normally we drive from the device and the SIB to do the communication between the various N channels that are available from the device to the system. System is in the sense 5G system, let's say, and in this case it will be 5+, whatever, advanced 5G. So are there any SIP defined by the device manufacturer? Do you have any specific band they have in S-band, which has become the capability to bring the device? And how will it handle if it is not a 5G G node, it's some H node, I don't know what that node will be. Is there any thought on that? Do you have any pointers to that in public?
I mean, so far what we have addressed is really handover management with respect to, say, the latest 3GPP features. What you saw in the test beds were work that was done in the open air interface. So yes, there are contributions from companies, but we are not really integrating an actual UE with the NTN capabilities in this type of work. We have some other work where we, of course, exchange with companies, but that's not part of the scope of the work we presented. Yeah.
Okay, so you'll stick to the non-standard access for the time being, with 5G being the G node being the primary point to access, whether it is through TN or NTN.
Right.
Like it could be direct, right? Device direct to satellite, D2S or what they call, or you are going to
Direct to
use UE
device.
only all the time. You have to use
It
both,
is.
right? If you have to connect between the two.
So I think it was explained. We do have the XN interface. We assume to be the path where you have two G node Bs, whether it's the terrestrial or the non-terrestrial G node B that is actually communicating. We do make assumptions in the simulations with respect to the G node B being on the regenerative payload, where you have direct-to-device communications. Yes.
Got it.
Thank you.
Thank you. Thank you for
We have to thank the speaker for all the four speakers that have done, and of course the Fraunhofer participant, but all the speakers, because they've done. I don't see. They've done a great job, and we have been very lucky to secure your talk today. So both topics are somehow related. So thank you so much. I would like to ask you if, okay, so we will just one microsecond, let's say, to share my screen and to show that let me see, just a second, your video presentation will be made available on the satellite working group page here. We have also other events and other webinars, so participants can download and see what the other events. And then our web chair, Professor Vajjafar, will help me to integrate your video presentation here. First of all, I will share with you, and then we will integrate here. I'm just asking in case you like to share also the slides, because people are asking, and then we can put it together with the video. If you like, you can provide other ways. It's up to you. We don't. So you decide you decide what to disclose. Okay. So now I think time is over. We have done a little bit longer, but we really enjoy, and I'm sure we will take advantage of all the information that the two groups presented today. Thank you very much. Thank you very much, and see you in another occasions.
Thank you so much.
Thank you.
Thank you.
Yeah.
Thank you. Very good presentation. I appreciate it.
Thank you very much.
Thank you.